Washington State University. Go Cougs!
Hello and welcome back to the course on Statistical Inference. We are in Module 2 where we're talking about different classification methods, and in the second part of Module 2 we'll be looking at the naive Bayes classifier. Now naive Bayes of course is based on Bayes' rule, which was developed by Thomas Bayes here back in the 1700s, but is the basis of a very powerful classification method. Now to understand naive Bayes a little better, we're going to have to do a little bit of review of probability and Bayes' rule. So here is a version of Bayes' rule that's tailored to our particular task of predicting an activity based on features or sensor data. And Bayes' rule basically says that if you want to compute the probability of a class given features or an activity given sensor values, then you can rewrite that as a formula based on three different probabilities, namely reversing the conditional probability and computing the probability of the features given the class, multiplied by the prior probability of the class, and divided that by the probability of the features. So in terms of an example, if we wanted to compute the probability that the activity is play, given specific values for the sensor data features, yaw, pitch, roll, rotation, acceleration, etc., then we can rewrite that as computing the probability of those features given that the activity is play times the probability that the activity is play given no other information, divided by the probability that those particular features would have those values, again, given no other information about activity or anything. So that is how we use Bayes' rule in order to turn the question around from a kind of a prognosis to a diagnostic type question. Now if we wanted to use this to do classification, then basically what we do is we compute this probability of class given features for every possible class we could consider, say in our case work and play, and whichever one has the higher probability, then that's the class we would predict. So essentially that comes down to computing this function where we compute, this is essentially the numerator of this probability. We compute that numerator over all possible classes, and whichever one gives us the largest value, that's the class we predict. Now we aren't computing the denominator because the denominator is the same no matter which class we are computing. So since we just need to know which is the largest, we don't have to actually compute that denominator probability. If we actually wanted to know what the exact probability is, we wouldn't need that denominator. But again, for just doing a prediction of a class, we just need to know which of the numerators is the largest. So as an example, again, if we wanted to compute the class given a particular set of features, we can use Bayes' rule to compute the probability that those features would show up given a particular class value times the prior probability of the class. Now this is still a very large, what's called a full joint probability distribution, and in order to compute this, we'd have to know the probability for every possible setting of sensor values over every possible class. And since these sensor values are real numbers, that's essentially an infinite space, and even if we were to, say, discretize it in some way, it would still be a huge number of probabilities that would be very hard to estimate accurately from the data. So this is where the naive part of Bayes comes in, and we're going to make an assumption about these features that will allow us to compute this a little bit more easily. So the naive Bayes assumption is essentially that we're assuming that all of these features are independent of each other. Now, if that's the case, then this full joint probability distribution becomes just the product of a bunch of very simple single feature probability distributions. Namely, instead of the probability of all the features given the class, we're going to look at the individual features or the probability of a particular sensor value given a class. For example, if we wanted to know the probability of a particular set of sensor values given the activity of play, we can estimate that by just computing the product of all of the individual sensor values. So just the probability of yaw equals 1 given activities play times probability of pitch is 2 given activity of play, and so forth. And the general idea is that these probabilities will be a lot easier to estimate from the data. So we basically say for all of the examples where activity is play, what proportion of those examples have a yaw of 1. So that is the naive Bayes assumption that all of the features are independent given the class. That assumption is usually not true. Usually the features have some dependency among each other. For example, the acceleration in the x direction probably is related to the accelerations in the y and the z direction. If you're moving around, they're all going to be moving. But again, this assumption will allow us to simplify things considerably, and generally it doesn't modify the appropriate class prediction too much, and we still get a pretty good classifier out of it. So that brings us to the naive Bayes classifier, where essentially we're just plugging in for this full joint probability distribution our naive Bayes assumption that we can estimate that distribution by the product of all of the individual single feature probabilities. And then, of course, we're also going to multiply that times the probability of the class, and that will give us our numerator, and we're interested in which class will maximize that, and that will be our final prediction. So, for example, if we wanted to know which class, work or play, is going to maximize this, we would compute the probability of each of the individual sensor values given that class times the prior probability of the class. Do that for work and then do it again for play. Whichever one's larger, that's the prediction we'll make. Now, since our features in this case are all numeric, we are going to actually estimate or assume that they're Gaussian distributed or normally distributed. And so these probabilities, these individual probabilities here, are actually going to be Gaussian. So we're going to basically compute the mean and variance of all of the yaw values for a particular activity, and then use that Gaussian probability for whatever new values that we're trying to predict. And then the prior probability on the classes is just going to be estimated from the data. The prior probability for work is just the proportion of activities that are work over all of the activities, and likewise for play. So I know that's a lot of math, but that'll give you the theory behind the naive Bayes classifier. But now let's look and see how we can implement it within the scikit-learn module. So in your course materials, you should have a file called naivebayes.py, and that contains the naive Bayes classifier applied to our sensor data. So in this case, we're not going to be visualizing the result. We're just going to print out the accuracy, final accuracy. So we don't need a lot of the other modules like matplotlib or the NumPy modules in this case. So all we're doing, again, we're importing the read data in order to read in our data. And from the scikit-learn module, we're importing naive Bayes and the metrics module, which contains our method for computing the accuracy of our predictions. So as usual, we're reading in our data. In this case, we're actually going to go ahead and read in all 9 of our sensor sensor values, yaw, pitch, roll, the 3 rotations and the 3 accelerations. And then, of course, in the Y array, we're going to be storing the values of the classes, 0 for work and 1 for play. Then from there, it's fairly simple. As we did for the nearest neighbors, for naive Bayes, we create an instance of the classifier, and then we fit the classifier to the data. Now, notice that we're using the Gaussian naive Bayes. Again, this is because we're assuming the features are Gaussian distributed, and if you have numeric real values for your features, that's the best choice. But there are other choices like Bernoulli or multinomial if we have, say, Boolean or discrete nominal values. But since the features are all numeric, Gaussian is the appropriate choice here. So after we fit the classifier to the data, we then predict on the same data using this classifier, compute the accuracy score, and then output it. So let's have the results here, but let's go ahead and see this in action. So here we are back into our directory for source code, and here we're interested in the naive Bayes classifier. So let's run that. And you see that it outputs an accuracy of about 95%. So let me start up the notes again. So here's that output we just saw, and recall that for the nearest neighbors classifier with looking for 3 nearest neighbors, we achieved about a 93% accuracy using just 2 of the features, acceleration, X, and Y. So on the surface, it looks like naive Bayes is doing a little better, but of course, we're only using 2 of the features for nearest neighbor, whereas we could use all 9, and we didn't really spend time tuning this K value. We could try other values for K, and it might do better. But for now, naive Bayes is doing pretty well, and later on in the course, we'll do a little bit more rigorous comparison of classifiers using some statistics that'll give us a better idea of which classifier is actually doing better. Okay, so that's our treatment of naive Bayes. And in the next part, we'll be looking at yet another classification method based on learning decision trees.